we've looked at an instance of working with mathematical induction. And mathematical induction is a proof technique that is useful, once again, when we have infinitely many statements. So I'm going to write that here as a reminder. We have infinitely many statements. There are certain statements that sound like there are infinitely many of them, but what there actually are infinitely many cases of that one statement. So, for example, the sum of two even integers is even. Well, that's really just one statement, because we can clearly define what an even number is. It's 2 times some integer plus 2 times some other integer. And when you add those together, you can factor out a 2, and you can see that that result will still be even. So that can be done with the method of direct proof. But in some situations, it can't. And we're going to look at summation equations, which are cool and also very useful, especially in programming when you're doing loops or you're counting how the complexity of an algorithm. We need to do a lot of counting, and it's helpful to have summation formulas. So as our first example, let's say that we want to add up odd integers. So recall that an odd integer is any number of the form 2 times some integer plus 1. So 2 times an integer will give you an even number, right? So if I take like 2 times 7, I get 14. That's always going to be even because it's 7 multiples of 2. And if you add 1 to that, you automatically get an odd number, because we know that integers go even, odd, even, odd. Now here's one other way that we're going to represent odd integers, and this is going to be helpful. It's going to make things a little bit easier here, is 2 times an integer minus 1, right? Because if 2 times an integer is even at all times, and you subtract 1, well, you're going back 1, but that's going to be an odd number, because even descending down, we go, the current one is even, the one below that is odd, even, odd, etc. So if I wanted to add up odd integers, well, first of all, how many of them do I want to add up? Let's just say 1 odd integer. And 1 odd integer, well, that's not very exciting. That's just going to be 1. Now, of course, here I'm assuming that we're going to start at the first positive odd integer, because -1 is also an odd integer. So what about if I want to add the first 2 odd integers? Well, the first odd integer is 1, and then 2 is not an odd integer, but 3 is. So that's going to give me a result of 4. And I can do this for 3 odd integers. 1 plus 3 plus 5 equals 9. Okay, and we can keep on going, right? We can add as many odd integers as we want, but ultimately we're going to get to the point where if I add up the first n odd integers, well, that's going to be 1 plus 3 plus, depending on what n is, I mean, n, but let's say it's bigger than 3, then it'll be 1 plus 3 plus 5 plus dot, dot, dot. This is just to mean it's going to kind of keep on incrementing by 2s. And it's going to go up to the nth odd integer. Well, how does that look? Well, we don't know what n is, but in order to find out, we would have to take 2 times n minus 1, right? Because the second odd integer is 2 times 2 minus 1 is 3. The third odd integer is 2 times 3 is 6 minus 1 is 5. So this is a general way of us representing that nth odd integer. Now, this could become computationally very expensive, because if n is really large, let's say it's 1,000,000, that's a lot of integers to add together. So our curiosity might be, could we add up integers without adding them up? In other words, could we figure out what the sum is without having to add? And that's what we want to investigate here. So part of building some hypothesis is sort of experimenting and seeing if you can find any pattern. So it's all about patterns. when you're formulating a hypothesis. Okay, so let's do that. Let's first formulate our hypothesis by looking for better ways to perform this sum instead of doing the following. Okay, what we have here is, remember, we wanted to add 1 plus 3 plus 5 all the way up to 2 times n minus 1. And the way we compact that notationally is, instead of having to write all those plus signs, we have this summation notation. You may have seen this before. This just means add up or sum up. And we're going to add up what? Well, we're going to add up numbers of this form. Numbers of that form are odd, as long as I is an integer. And we're going to start with I equals 1. All that means is 2 times 1 minus 1. Well, that's 1. Then we move to I equals 2. So we add the I equals 2 value, which would be 2 times 2 minus 1, which is 3. 2 times 3 minus 1 is 5, and so on, until we get to the last value right here. We do that in red. So until we get to that last value, the last value, we don't necessarily know what it is. It could vary depending on how many we're trying to add up, but it's going to have the form of 2 times n minus 1. This is the nth odd integer. Okay, so the summation is just compacts all of that into a simple notation, just like when you say H2O, that's a simpler way to say water. And in mathematics, we also use abbreviations like that. All right, well, let's investigate this further. So we said this is computationally expensive for large values of n, and we're wondering, is there a more optimal way to do this? So my goal is going to be to generate this little t table, and in this table, what I'm just going to keep track of is, for different values of n, how does the sum work out? So here I'm going to look at the sum of that many integers. So we've already said that when n is 1, it's just the first odd integer, which is 1. Not very interesting. If n is 2, we're going to add up the first 2 odd integers, 1 plus 3, which is 4. We've already done that. For n equals 3, we did that. That was 1 plus 3 plus 5, first 3 odd integers, which is 9. Now if we do the fourth odd integer, 1 plus 3 plus 5 plus 7, that's going to give me 16. And then keep in mind that all we're doing in the next step is we're taking the previous set of values and adding the next odd integer. So I'm not going to, 1 plus 3 plus 5 plus 7 plus 9 is 16 plus 9, which is 25. And then 25 plus the sixth odd integer would be 25 plus 11, which is 36. Now, all I want you to focus on here is I want you to focus on kind of this input-output relationship. So given an input of n, can we detect a pattern in how those outputs are changing? So I see 1, 2, 3, 4, 5, 6 for the inputs, 1, 4, 9, 16, 25, 36. Now, the pattern's not always going to be immediately evident, but I hope you see here that these are perfect squares. These are perfect squares. In fact, 1, as it relates to the value of n, is just 1 squared. 4, as it relates to the value of n, is just n squared. 9 happens to also be 3 squared. 16 happens to be 4 squared, and so on. 5 squared and 6 squared. So at this point, we might think, instead of me having to add up the for the first 7 odd integers, I might just be able to take 7 squared and get 49. And I believe that that's going to be, for 7, I think I'm going to get 49. And we can kind of see that that does work, because 36 plus the 7th odd integer, which is 13, is in fact 49. So we have a hypothesis, but we don't yet have concrete proof. So let's formulate our hypothesis. We believe that adding up the first n, beginning at 1, the first n odd integers is equal to n squared. So that's what we're saying here. If you simply square the value of n, you get the same thing that you would if you were to add them up manually. So here we have a sum, And this is a quick computation. No matter how big n is, if this relationship is true, all we have to do is square that value of n, and we've got the summation. Now notice here that there are infinitely many statements that we would have to establish in order to make this claim be proven to be true. Infinitely many. In fact, when we say statements, here that means equations. There are infinitely many equations here. There is P of, well, the smallest the value of n could be is 1. We could just sum up the first odd integers. I know that sounds strange, but P of 1, which is the statement that the sum from I equals 1 to 1 of 2i minus 1 equals 1 squared. Then there's P of 2, which is, as you might guess, the first two odd integers that we're claiming is equal to 2 squared, and so on, right? And there are infinitely many such cases. So there are infinitely many claims, and we would need to spend the rest of our lives and never get to the end of this proof. Instead, we're going to do this by induction. It's a perfect candidate for it. Remember, the idea is this. P of 1, in our case, it's the base case down here, number 1. Prove the base case is true, n equals n naught. Our n naught, our initial case, is 1 because n can be as small as 1. And then P of 2, P of 3. And remember, we're not claiming that this important piece here is like smack dab in the center. This is just a visual representation. So we prove that the base case is true. Then we assume our statement is true for n equals k. Assume P of k is true. And then prove, based upon that the next case is true. So what we're doing here is we tip over the first domino, but how do we know that it tips over the next one? And even if it does, how do we know that that tips over the next one, and this goes on in an infinite sequence? So what we're going to do is we're going to just assume that there's some domino that you can tip over. In other words, assume that there exists a statement that is true. Now we already know there's one, and that's for n equals 1, but we don't want to incorporate n equals 1 in this arbitrary case because our goal here is to establish that any arbitrary domino for which the statement is true will always tip over the next one. And since any domino always tips over the next one, that is all we need to start the chain effect. That would mean P of 1 tips over P of 2, which tips over P of 3, which tips over, and so on. This goes into infinity. So assume the argument is true for some arbitrary case, n equals k. This feels troublesome sometimes, but remember, we already have one situation where it is true, but in this step, we want to establish the logic of dominoes knocking over the next ones. Then the induction step, use the assumption from the previous step to establish the statement is true for the next argument in the sequence, n equals k plus 1, which is the statement P of k plus 1. So we've established, or we believe, that the sum of the first n odd integers is n squared. So here we go. Let's do step 1. Step 1 says prove P of 1. P of 1 is the statement that the sum from I equals 1 to n equals 1. So the sum of just the first odd integer, that is equal to 1 squared. Well, we've already done that. We've already established that in our table. The sum of just the first odd integer is 1. Oh, by the way, I always put a question mark above that equal sign until I'm certain that they are equal, because I can't claim they are equal until they are. 1 squared is 1, and check that out. Yeah, 1 equals 1 is a true statement. So that checks out. And now we have to do the assumption step. Assume P of k. Now notice I'm not saying assume P of k is true, because P of k is by itself is either true or false. So by this, assume P of k is true. So what does that mean? Well, that means, i.e., we're going to assume that the sum of the first k odd integers up until that arbitrary case of odd numbers is equal to k squared. That value and that value are the same. Now, we have now the burden of proof. We want to prove p of k plus 1, i.e., we want to prove that the sum from I equals 1 to k plus 1, in other words, the first k plus 1 odd integers, the first k integers plus one more odd integer after that, that should equal, if our formula is true, again, notice the relationship between where the summation ends and the right-hand side of our formula, that has to be the same. So in this case, since the value of n is k plus 1, we would expect that the sum of the first k plus 1 odd integers would be quantity k plus 1 squared. So how do we do that? Well, the first thing we want to do is somehow establish or be able to use our assumption step. And here's how summations work. So the summation from I equals 1 to k plus 1 of 2i minus 1, so of the first k plus 1 odd integers, is 1 plus 2 plus ... plus the kth integer, which would be 2k minus 1. That's the kth odd integer. It's weird to say, I know. And then what's the k plus 1th? Oh, that sounds funny too. The k plus 1th odd integer. Well, that is the odd integer that you would get if you plugged in k plus 1 for I. In other words, 2 times k plus 1 minus 1. That is the k plus 1th integer. You don't need those parentheses there. I'm just putting them there to isolate them from one another. Okay, well, we already know something about this, 1 plus 2 plus ... plus 2k minus 1. We already know from our assumption step that this right here is the sum from I equals 1 to k of 2i minus 1. And what do we know that equals? Well, that equals n squared. We assumed that that was true, so now we can say, well, all of this equals n squared, but this pink, red, whatever you want to call it, this term is now separate from that and needs to be added on. Okay, so what's different, what we have to establish, is that when we add up, pick a different color here real quick, let's go with orange, that basically this expression ends up being the same result as k plus 1 squared. Notice our equal sign, the sum from I equals 1 to k plus 1, sum from I equals 1 to k plus 1. We want to show that eventually that equals k plus 1 squared. Oh, and I did make a little mistake here. I used n instead of k, but the sum of the first k odd integers is actually k squared. And you can do this one of two ways. You could either kind of not expand, but write the factorized form of this, or you could also state, well, k plus 1 squared is k plus 1 times k plus 1, which is k squared plus 2k plus 1. So we could either make this orange highlight look like quantity k plus 1 squared, or we could make it look like k squared plus 2k plus 1. Well, it might be easier if you're not, you have a harder time factoring. It might be easier just to expand the thing that you're trying to get and then expand what you have and show that they're exactly the same. So k squared, distribute, plus 2k plus 2 minus 1, and check it out. Don't you know, it's exactly what we expected. Oh, sorry, plus 1. And if you wanted to take this one step further, if you were really good at factoring, you could say, hey, that's the same thing as k plus 1 squared. But, you know, it's totally okay to expand out what you know you're expecting to get, and then you can avoid having to factor. Sometimes it's easier to FOIL than it is to factor. So what does that mean? Well, again, we need to state our conclusion. Since the inductive step is true, in other words, p of k plus 1 is true, p of 1 is true, we now know that if the summation works for one value, it always works for the next value. And by value, I mean if it works for the first k integers, then it's going to work for the first k plus 1 integers, which means every domino always knocks over the next one. Since p of 1 is true, that means p of 2 is true. Since p of 2 is true, that means p of 3 is true. So on. There goes the chain. So our conclusion is that the sum of the first n odd integers can be found by simply taking the value of n and squaring it. There's our definitive proof. We're not doing anything by example. The example that we did here was just to establish a pattern and for us to create a hypothesis. Let's go ahead and stop there, and we'll take a look at one more summation example. Namely, what about summing the first n even positive integers?